Lab 6 titled Magnetic Molasses by Jackson Greencorn. Let's get into it. For a brief introduction, the purpose of this lab is to observe current induction by dropping a bar magnet into a bar of aluminum foil, more like a roll instead of a bar. In doing so, we have physical observations and compare it to a computational model made in GlowScript. This system is the tube and the magnet, and the surroundings include the environment and the world around it. From my results, we have that the experimental time average was 1.588 seconds, and the computational timing is 1.12 seconds. For our theory, we have the Biot-Savart law, which describes the magnetic field produced by a current-carrying wire that depends on current, distance, and orientation. We have Faraday's law, which describes the change in magnetic fields induces a voltage proportional to the change in magnetic flux and an induced voltage that opposes the magnetic flux. And then finally, we have Newton's second and third laws stating that the net force is equal to the change of momentum over time and that for every action, there's an equal opposite reaction. We're mainly only using this for the gravity section. For our experimental procedure, we are going to drop a bar magnet into a roll of aluminum foil. We're going to record the time from the second it passes the entry to the moment you see it come out. Take the notice to the slow descent from the induced currents. Like as soon as you drop it in, it's going to slow down. It is weird. And then we're going to repeat this a couple more times to get more accurate timings and observations. Here's my entire computational model, the first part of it anyway. You can see on the left side, we start with mu naught over 4 pi, resistivity, gravity constant. We're creating the plot, and then going through this, we're actually creating the geometry of the aluminum tube. And then going through on the right side, we're actually creating the geometry and the physical aspects of the bar magnet, giving it mass, its mu. And then we are starting the dipole moment, defining the change in flux. And then on the second right here, here's the rest of it. On the left, you'll see that we are iterating over time, giving a gravity vector, giving the magnetic force, and then using that to calculate the change in flux, giving a current around a ring. And then we're using all of that to create magnetic force and then creating a net force from the gravity and magnet, updating velocity, updating position, and then finally plotting it all on a curve that you'll see over here as exit time minus enter time as our result from what we saw previously. Here's our outcome, computational versus observed. You'll see over here on the left side, it goes straight down, right? And this is actually where the force of gravity is greater than the magnetic force, but right here it dips back up and is constant for a long time. Velocity is even, means there is no acceleration, which proves that the magnetic force is equal to the gravitational force at this point, that there's no acceleration. And then once it gets towards the end of the tube, magnetic force kind of takes back over, and we'll see that again we have that 1.12 second outcome versus the 1.588 seconds from the observation. And actually, before we get into the next section, the reason that the average time is actually higher than the computational time is partially due to the resistivity. The resistivity is given to us. We're told to use the resistivity in the code. We didn't measure resistivity of the aluminum foil or induced current for the observation or physical methods. But something else, the bar magnet could end up spinning, which changes the direction of the magnetic field and induced current, which changes velocity and such. So in the computational model, it is straight up and down. In the observations, it could have spun, flipped, done every sorts of different things to change. So for the what if sections, well, for the answer to what if number 1, the resistivity of the conductor were reduced. That would increase induced current, which would slow the magnet down even more by strengthening the opposing magnetic field. And then the what if holes or slots were cut into the tube, well, then there would be gaps in the induced current, which would weaken the opposing magnetic field and let the magnet fall faster. Thank you for your time. This has been Lab 2, Magnetic Molasses. Thank you.